Okay, so I'm continuing with the class. Last Wednesday, if you remember, we had started off with chapter number 4. I just gave you a brief introduction. Okay, so we'll continue with this. Now, we were talking about control systems. I gave you some examples of control systems. Why we need to control. Okay, it's very important to control because we need to maintain the quality of the product that is being manufactured, and by using the sensors we will measure and compare and then control it. It's very simple, similar to how you are thinking of driving your car or maintaining the temperature of water in the from the heater. So based on this, we understand that every control system consists of an input, and the input signal is then used by the control system, and thereafter the output is produced. All control systems are dependent on something that's called as a feedback path. Okay, I'll explain to you what it means. Now, based on this feedback path, a control system is classified as open loop control system and closed loop control system. So from these words, you will understand that there's something to do with a circle being completed. Okay. So when we talk about this particular diagram that I have given to you here, it is an open loop control system because there is no path connecting the output back to the input. Okay. So we are going to first think about an open loop control system. What is the meaning of open loop control system? So you see here, okay, every control system has a very typical block. What is this block? Here we will be bringing the measurement. Okay. And here we will have something that is called as the desired value. Desired value. Now, every time, okay, the measurement is going on continuously, it will be compared with the desired value. For example, okay, I want a water heater, okay, and the temperature of the water should be equal to 75 degrees C. This is my desired value. I want the water to be heated only up to a temperature of 75 degrees C. Continuously, the measurement temperature will be, we will use an RTD and we will continuously monitor the temperature of the water. Every time, these two values will be compared. The desired value will be compared with the measured value. And according to the difference, okay, let us say, for example, in the beginning, in case 1, let us say that Tm is equal to 28 degrees C. What do you notice? You notice that the difference between the desired value and the measured value is very high. So this signal, this information is given to the controller, okay, and accordingly what it will do, it will go and switch on, it will switch on the heater. It will switch on the heater. Heater will be switched on. When the heater will be switched on, what will happen? The temperature of the water will start to increase. Okay. Now, as soon as the temperature of the water will increase, what is going to happen? It is going to go up from 28, it will increase to 50, and then finally it will reach 75. Now, when it reaches 75, that means it is now matching. What was your desired temperature? 75. Your measured temperature is also 75. So the aim of your process is satisfied, and therefore this information will make the controller to switch off the heater because you don't want to heat it beyond 75. So this example, I have told you what does the controller need, and according to the decision, according to the difference between the measured value and the desired value, the controller takes a decision of switching on or off. So this is an open loop system. Now here you see, this is the desired value. Here you have the disturbance, and this particular circle that I am drawing with a cross is called as a summing point. Okay, so here you have the set point, that is what is your desired value. So what is the meaning of set point? Set point means desired value. This is usually set by the operator. Then here you're getting the input, and according to that input, the comparison, the plant or the process. Now we call the process, we also use the word plant. When we say plant, it means the entire system where the process is being carried out. And according to the decision, the controller will be making the control variable or the heat to increase or decrease. So we are calling this an open loop control system. Why? Because there is no check for measuring. Okay, we are only switching on the heater or switching off the heater. It's only going by on and off. There is a decision according to which the plant is going to work. But we don't have any way of taking a feedback. There is nothing that is going back. Okay. Now, what is the another example of open loop control system I can give you? I can give you another example of open loop control system is of a simple washing machine. Okay, what is the purpose of a washing machine? We have this appliance in the house and we say it is automatic, correct? Now I have a question to ask. Does your washing machine measure the brightness of the cloth? Does it measure if the cloth is clean or not? Is there any sensor to measure?
No, no.
No. So that is the meaning, that is what is meant by being an open loop control system. So the washing machine is automatic. It is an open loop control system which is producing clean cloth, but you are not measuring it and you are not giving any signal back. All that you are doing is you are allowing the machine to work how? You are allowing the machine to work on time. On time. That means you say you load the clothes, you load the detergent, and you turn the machine on. And what is automatic about the machine then? The entry of the water, the stoppage of the water, the entry of the detergent, the time taken for the drying, the spinning, all of that is automatic. But how are these actions coming? That is because it is set by time. Okay, so a washing machine is an example of an open loop control system which is automatic. However, we have no sensor to check the brightness of cloth, and that is why we classify it in the as an open loop system. Okay, another example I can give you is of a traffic signal. What happens in a traffic signal? You have crossroad, okay, and perhaps here you have a traffic signal. Now, there may be some car here, car here, car here, and car here. Now, depending upon the time, okay, the color of the light of the traffic signal is changing from red, orange, green, and it is being repeated. So, it does not check whether there is a car on the other roads, okay. It is just changing the color according to the time that is set. Okay, what is the purpose of this traffic signal? It is to make sure that there is no accident on the road and all the vehicles can move smoothly. But there is no sensor in an ordinary traffic control system. There is no sensor to check if there is a car on the road or not. So even if there is no car here, let's say there is no car here, okay, still the signal will change. So you have to wait till the color is changing, and then the signal will allow or it will change color. When it becomes green, you are going to move. So this is also an example of an open loop control system, which is dependent on time. Now, I know there are some cities, there are some traffic signals which have been made smart. You must have seen a lot of examples. What are those smart traffic signals? Where they will have a load cell. You know the strain gauge, no? They will have a load sensor on the road. And the moment this load sensor is giving a signal that there is no car, the traffic signal is going to allow the car in the opposite road to move. Now that's a smart one, that's a closed loop one. But the usual ones that we see on roads are the open loop traffic systems, where the light is changing according to time and allowing the traffic to move. So remember the point that I told you. Open loop control systems, open loop systems are dependent on what? They are dependent on time. Okay. So going back again, open loop control systems are open because there is no feedback. Okay. Then they are only dependent upon time. Now they may be cheaper or they may be easier to design. However, they have the disadvantage that we cannot use this system in a refinery. In a refinery, you want precise control. So whenever you want precise control, you have to go in for having a closed loop control system. Closed loop control system is also called by another name, that is feedback control system or closed loop control system. Now, why do we call it as a closed loop control system? Because if you look into this diagram, okay, you will notice that if I draw a simple diagram, you will notice that this is your process, and then the measurement is taken back and then it is given for comparison. So it's not open anymore. We are measuring and then we are comparing it. So a closed loop control system is also called as a feedback control system. What is the meaning of the word feedback? You see this line, the output of the process, that means the temperature, the pressure, the flow, whatever the signal may be, is measured and then sent back for comparison. So each time the controller takes a decision, it is real time. It is depending on what is happening in the process. Okay, so closed loop control system is consisting of a feedback path. This path is called as the feedback path. Now let us look at all the parts of this closed loop system. The parts of the closed loop system are, let us start from the right hand side. Okay, the first one is called as the process. Process is where the steps are taking place. That means maybe it is heating the water. So there is a vessel inside which you have a heater coil and you have the water being brought in and the water heating is taking place. So that is an example of a process. Now, when we talk about process, we have so many, like right now you are studying. So you are in the process of learning, right? So in this process of learning, what do? We have an exam. What is the purpose of the exam? It is to check whether you have learned or not. And thereby, if the grades are not enough, you are going to repeat the course. If the grade is good enough, that means you have learned, you will go ahead. So everything in life has a process. Even in your body, there is a heart which is pumping blood. There is a lungs, respiratory system. They are all processes, breathing process, digestion. So process can be defined broadly, life process, biological processes, chemical process, physical process, economics, so many things, everything is a process. What is a process simply meant? It is a series of steps taken till you reach a particular aim or end. Okay. Now, from this process, we will measure a variable. What is the meaning of the word variable? Variable means varying means changing, no? So there is some variables in the process like temperature, pressure, flow, level. These are all variables. So those process variables which describe the process. Like if I'm saying heating, if my process is heating, what will be the process variable? The process variable will be temperature. If the process is filling the tank, if the process is filling the tank, can you tell me what will be the process variable?
The force.
Okay. So according to the process, we will be describing the variables.
Force
That
or
variable,
volume.
filling the tank means you will have to check the level. No? Like when you're filling petrol in the tank, how do you check? You check by the needle, whether the tank is full or half or like that. So you're checking the level. So that process variable like temperature, level, flow will be measured by the sensor. And you have learnt about all the sensors. So you know what is happening. The sensor will measure it, and that measured value, the measured process signal, which is called as PV, capital PV, will be fed to this block. What did I tell you is the name of this block? This is called as the summing point. Summing point. So in this block, in this particular point, you are bringing in two information. One is the feedback about the measured process variable. The other is the set point, which I told you also means desired value. So in this block, you see there is a plus sign here and a minus sign here. What does it mean? It means that the output of the summing point is called error, is called controller error, and this error is equal to set point minus the measured value. So according to this error, this controller will take a decision. That decision is called as the controller signal output or CO. Okay. Then this controller output will make some action. The controller output will make some action. For example, if we are talking about heating of water, it will take an action by making the heater. Okay, so then here we'll have the heater. The heater will be switching on or switching off. So this device, okay, so the block that comes after the controller, I'm telling you now, is called as the final control element. So when we are talking about the heating of water, you can think of this example as a heater. If you are talking about filling the tank, what do you think this element will be? It will be a tap. You know, like when you go to fill petrol, they will see that the tank is getting full, and what will they do? They will switch off the valve so that no more petrol is flowing. So here you can think of another example of final control element as a valve. Valve, or we can think of the final control element. Suppose it is a process of cooling. Cooling means you want to decrease the temperature. So maybe you can have a fan, or maybe you can have an air conditioner. So the controller is making some device to take the decision. The decision is coming from the controller, but the action is taken by some other device. That device is called as the final control element. So if we think about driving the car, when you see that the speed limit is less than the speed of your car, what will you do? Your brain will take a decision and make the leg to press the brake. So that is a final control element. The device that takes the action as decided by the controller is called as the final control element. Then the output of this final control element is called as the manipulated variable. Can anybody tell me the meaning of the word manipulate? Manipulate means adjust. Manipulate means adjust or change. Okay, so here the output of the final control element is called as a manipulated variable, which is then given as input to the process. So you know that the heater will switch on, so more heat will be given. The valve will open, so more petrol will flow. So like that, the manipulated variable is the output of the final control element. Now, while this process is being carried on, there can be something that is called as disturbance. Okay, what is disturbance? Let me give you a very simple example. Let us say that we have a room, we have a classroom, okay? There is a door here, this is a door, and there are two windows, and there is an air conditioner system, okay? And according to this, the set point of the temperature we are keeping is 24 degree C. This is supposed to be the ideal temperature, okay? So now the measured value, that is the measured temperature of the room, is also 24 degrees and the room is cool. So the process is carried out, is going on smoothly. The temperature is measured, compared with the set point, and the air conditioner remains switched on. Now, during this time, suddenly, one of the students is going to open all the windows. What will happen? What will happen to the temperature in this room? If it is summer, you can imagine what will happen. Suddenly, because you opened the windows, hot air will enter into the room. Because this hot air is entering into the room, what will happen to the output from the sensor? The sensor output will be increasing. Earlier it was 24, now maybe it will become 30 or maybe it will become 35. Okay, so this particular action of making the variable to increase or decrease suddenly is called as disturbance. It's called as disturbance. And whenever there is a disturbance, what will happen? This process variable measurement given will change. Again, the error will be increasing, making the controller to take action. And so what you notice is, for any disturbance, the controller is going to take action. That is the advantage of it having feedback. So every time the controller is seeing that the process variable is not matching the set point, it will make the final control element implement the decision of either switching on the heater or switching it off, depending on the size of the error. So these are all the parts of the closed loop system. In simple, when I think of a closed loop system, I can draw the diagram like this. Always start with the process. I'm drawing this so that you are also getting an idea. Always start with the process. Here you have the controlled variable. This is measured by a sensor. Okay, and then the process variable that is measured is given to a summing point, which is also getting an input of the set point. You have a plus and a minus sign here. This output, that is the error, is given to whom? It is given to the controller. The controller takes a decision by using the final control element and sends it to the process. So here you have the controlled output and here you have the manipulated variable. Always remember to allow the disturbance to be felt by the process. So this is a simple diagram of a closed loop system. So you have to, you remember the parts. The first one is the process, then comes the sensor. You have the summing point where you're calculating the error, which is equal to SP minus PV. So remember, the plus sign is here and the minus sign is here. Then the controller produces an output, which is the decision, which is implemented by the final control element, and the output of the final control element is called as the manipulated variable. So the advantage of closed loop system is that it will always make sure that these two values are matching. Now let's look at the differences between closed loop and open loop. So if you see the first difference, the open loop control system, the control action is independent of the desired output because we are not feeding it back. Whereas in the closed loop control system, the control action is dependent of the desired output. In open loop, there is no feedback. In closed loop, there is feedback. These are called as non-feedback control systems. These are called as feedback control systems. Now, what are important in these to remember is the first one. Then it is easy to design. Closed loop control system is difficult to design because you know you have to design the controller. You cannot simply place a switch there. These are cheap. Closed loop is expensive, but open loop is inaccurate and closed loop is accurate. I'm adding one more point here. The control action is dependent on time, whereas here the control action is independent of time.
Or like condition air, Doctor.
Yeah.
One example of this condition air.
Yes. So now these are the differences. Now this is a very standard question asked almost every time, but don't only memorize them, try to understand and then write down the differences. Okay. So write I have tick marked the important ones. Okay. All of these are the important differences between open loop and closed loop system. And here are whatever I explained to you written in words, definitions and terminologies. What is the meaning of controlled variable? It is the output quantity of the system. Like I told you, it can be level, temperature, etc. What is set point? It is a desired process level. What is the process variable? It is the actual process value. Okay. And it is indicated by PV. What is the error signal? The difference between the set point and the process variable. Then comes manipulated variable. It means maintaining the control variable at set point. So manipulate means adjust so that the control variable is equal to the set point. What is a process or a plant? It is a piece of equipment or a set of machine parts functioning together to perform a particular operation. For example, a reactor, in which a reaction is taking place by keeping the temperature and the pressure constant. So that will be an example of a reactor. Or also another example which is very common for you is distillation column, distillation tower. What is a system? A system is a combination of all the components. So when we draw the block diagram of the closed loop control system, there is process, there is a sensor, there is a summing point, there is a controller, final control element. So when you put all of them together, we call it as a system. Now, what is a disturbance? Oh, I gave you an example. Now, how do you explain it? A disturbance that tends to adversely. What is the meaning of the word adverse? Opposite. Adversely affect the value of the output of a system. So if the heater or if the room temperature is kept constant, what is happening when you open the windows? Hot air is coming in and it is making an opposite effect on the temperature. Okay, so disturbance is something that is undesired, but however, in every practical process, it is going to be there. You cannot avoid a disturbance. So disturbances can be of two types. One which is inside the system, within the system, that's called as an internal disturbance. An external disturbance is generated outside the system. Okay. For example, the example that I gave you of the temperature suddenly changing because of opening the windows, that is an example of an external disturbance. Okay. And internal disturbance means it is some problem or it is some disturbance in the final control element or in the process, in the sensor, or there can be some problem with the controller. Such disturbances will be internal to the system. External means what is not in the system cannot take care of it directly. It has to go through the process of feeding back the signal, comparing it, and then going ahead. What is the meaning of feedback control? Feedback control means it is correcting the error. See, when there is a disturbance, what happens? The process variable is increasing or decreasing. So you are getting an error, and then the error is correcting by the decision taken by the controller. So that's why we say feedback control means it is correcting the error. Following means after the disturbance. So basically, the system is allowed to have a disturbance, and then you're making a correction on it. Okay. So this part is not there. I'm not going to take this part. So until here you will have, okay, and then we proceed to go ahead This is also not included. Okay, so we're starting from here now. Okay, so we have discussed about what is a control system, what are the two types. One is open loop, the other one is closed loop. And we are going to focus our attention on closed loop controllers, because you will be looking at controllers that are used in the different processes in a refinery, where the process itself is very stringent. That means you have to make sure that the quality and the quantity are maintained constant, and you cannot use open loop. We have to go for the use of closed loop. So we are focusing our attention now on only closed loop controllers. So again, this is what we are going to focus our attention on, that is closed loop control systems. So the first example of a closed loop control system is an on-off controller. Now, from the name itself, you will understand that the control action, what we are studying now is what strategy is taken by the controller. How does the controller take a decision? What is the mathematical, is there any mathematical operation that is being carried out? How is the decision taken? That is what we are focusing our attention on. So the first type of strategy that we are looking at is called as the controller, which takes a decision to either switch on the final control element or switch it off. Okay, so we are going to look at an example of a water level maintaining. Okay, so let me explain the process to you first. Here you see you have a tank. Okay, and in this tank there is water. How is the water coming in? The water is coming in through this valve. This is a valve. The water is being allowed to come in through this pipeline. In the pipeline, you have a valve. And the input flow rate is called as Q in. Okay. The input flow rate is called as Q in. Now, we are also allowing the water to go out. The flow rate of the output is Q out. So there is a continuous withdrawal of the water. Water is coming in. Think of this as the overhead tank in your house. So water is allowed to come in, and then whenever any tap in the house is open, the water is being drawn out. Now, what is the aim of this process? The aim of this process is to make sure that the water is always maintained at this height. So this is this level that I am showing you here is the set point. What is the meaning of set point? It is the desired value. So in this case, it will be the desired value of the level. Okay. Now, we need to measure, because this is a feedback control system. So every time the level has to be measured. So here is your level sensor. P1 is the level sensor. Now, how does this level sensor work? This level sensor is kept at the bottom of the tank. Okay. This level sensor is placed at the bottom of the tank, and it is written by the letter P1. So it is actually a level sensor, but it is sensing the pressure. Now what will happen? Every time the level of the water in this tank is going to rise, the pressure at this point will also increase. If the tank is empty, the pressure will be equal to atmospheric pressure. But as the water starts to fill up, the pressure inside the tank will increase. That means actually the rise in pressure is the rise in level. How do we understand that logic? So let's look at the pressure, that particular sensor. Okay, so the pressure is equal to rho into G into H. What is H? H is the level of water in the tank. Okay, rho is the mass density and G is the gravitational acceleration. So according to this rule, we know that, you know this, when you have a U tube and if you have checking the pressure, the difference in pressure will be, here you have pressure P1, here you have pressure P2, then delta P is directly proportional to the difference in the height. So the same logic is being used in this case also, and we understand that the height of the liquid in the tank is going to be directly proportional to the pressure. So that is why we are using this particular sensor. Okay, so this particular sensor again, so I told you it's a sensor. Now along with it being a sensor, it is also a switch. It is a switch. You know what a switch does. Switch is either making something on or it is making it off. So if you see in this picture now, this is the completion of that particular sensor. This is the switch. And this switch is connected in the line of a power supply. Okay. So every time the switch is open, there is no power supply given to the valve. This valve, okay, is called as a solenoid valve. Solenoid means what? Does anybody know what is the meaning of solenoid? Solenoid means it is a piece on which there is a coil winding. Okay. So whenever you give power here, whenever you give power to this coil, this particular piece starts to behave like a magnet. Starts to behave like a magnet. So here also we have a solenoid valve because there is a solenoid inside this valve, and to the other end we have another iron piece. Where is this iron piece? This iron piece is in the pipeline. Okay. So when there is no power, this piece is blocking the flow of the water. When there is no power given to the solenoid, that means this piece, this solenoid is not going to be like magnet. It is not magnetized, it is not having any energy. So this piece will block the flow. There will be no flow. Okay. Now, whenever the switch will close, whenever it will close, what will happen? Whenever it will close, what will happen? The power supply will be given to the solenoid. When the power supply is given to the solenoid, this piece becomes like a magnet. Then the piece that is kept ahead or above, which was blocking the flow, it will get attracted. That means it will be pulled down. Now it will be pulled down, and then you will have the space here open, and it will allow the water to flow. So that is the solenoid valve that we are using here along with the switching action. Okay. Now, how is this switch initiated, or how is the switching action made possible? Now, every time the level of the water, okay, reaches up to L2, every time the level of the water reaches up to L2, this switch will open. Now, like it is now, it is open. So every time the water level reaches L2, the switch will open. If the switch is open, there is no power and there is no inflow. Okay. Now, when there is no inflow, what is going to happen? The level of the water in the tank will reduce. Very good. So, and then as it is reducing, it will come to L1. The moment the sensor is getting the signal that the level has reached this value, this switch is going to close. It is going to close. When it closes, the power will go on, the solenoid will be energized, and the valve will allow the water to flow. Again, what will happen? As the water level is increased, water will enter into the tank, it will level will start to rise, again it will reach L2, again the switch will open. So this process is going to go on continuously. So we are allowing the water flow to be coming in sometimes, stopping sometimes, coming in sometimes, stopping sometimes. And what is our aim? Our aim is to maintain the level between L2 and L1. So This particular control system is allowing the water level to remain such that the tank is not becoming empty or it is not becoming overflow. There is no overflow. Now come to think of what's happening on the side. Are we able to keep the level at set point exact? No. Because it is only going to be between these two levels, between level L1 and L2. We cannot keep the level exactly at the set point because the controller is taking an action only at these two positions. When it is at L1, it is allowing the flow to come in. When it is at L2, it is closing the flow. So only two things are taking place. We are not able to maintain the level at the set point. So this particular control system is depending on the sensor which is acting as a switch. Whenever the level is at L1, the height of the liquid will be above the switch and it will make the switch to open. Whenever the level is at L2, the switch will close and no more water will be allowed to flow through. So this valve has to be correctly sized and it will make sure that the level is always going back. That means you have L1, you have L2 and this is your set point. We are trying to keep it within the range of L1 and L2, but we are not able to keep it exactly at the set point. Okay, so this type of control action that we are studying or strategy that we are studying is called as an on-off control system. Okay, now the problem with this control system is that it is making the system to become slow. Because it is waiting for as the level is increasing, the switch is switching on, switching off. Now imagine if you have a very large tank, what will happen? It will make the system to become slow. Now let us try and understand how we can look at the variable. What is our variable here? What is our process variable? Is level. The process variable is level. Okay. So from this diagram now, let us try to understand what are the different parts of this closed loop system. What are the different parts? So this tank you are seeing is the process. Okay. Where is your sensor? This is your sensor. Okay. Now, where is your controller? This whole arrangement becomes the controller because it is taking a decision to switch on and switch off now. So this becomes your controller and this device becomes the final control element because it is taking the instruction from the controller and either opening or closing and allowing the flow to come in to the tank. Now here, what is your process variable? Your process variable is the level. Level is the process variable. Okay. I have only one question now. What is your manipulated variable? Manipulated variable. Which variable is being manipulated? I will just remind you again. The final control element is taking the action according to the decision given by the controller. So it is either switching on or either it is allowing the flow or it is blocking the flow. That means the manipulated variable is Q in. Because it is this flow of water into the tank is being adjusted. Either you allow it to come in or you close it. So this is the variable. Variable means something that is changing. The flow is changing. So the Q in becomes the manipulated variable. The process variable is level. The final control element is the valve. And here you have a combination of the sensor and the controller together. Now, from here, we are going to draw the graph for the process variable with respect to time. Now, the line in the center is the set point. This is the value at which you want the level to be kept constant. But we have two extremes. One extreme is L1 and the other extreme is L2. And the process variable is cycling. So we start maybe at set point and then the level goes down. When it goes down, what happens? The switch is opening, allowing the water to come in, and thereby the level starts to increase and it reaches L2. When it reaches L2, what happens? When it reaches L2, the switch is going to close the valve and the level will start to again decrease. And this is the cycling that you are seeing. So the output, the on-off controller is going to make the process variable to cycle. Cycle means it is never going to be at the set point, but it is continuously going to vary around the set point depending on these levels or depending on the limits that you are giving. The advantage here is you will not have the tank becoming empty or you will not have the tank overflowing. Both are extreme conditions. So this is an example of the on-off control system. The on-off control system, temperature control, most commonly used on-off temperature control system. And then this cycling is called sinusoidal because it looks like a sine wave, no? Like an AC signal. That's why it's called as a sinusoidal signal. And then the advantage they say is when you have a large heater system, it is okay to use the temperature control system, the on-off controller. But the problem, what is the disadvantage? It will not keep the value of the variable at set point. So advantage is you can use it for heater systems, water heating systems or any heating systems which are very large in size. So that is the example of an on-off controller. So when I say on-off controller, you can also think of this as a controller which is having two positions. 100% is on, 0% is off. Okay, so you can have completely on or completely closed. There is nothing in between. That means the valve, if this is the valve, this valve is either fully open or it is completely closed. We don't have a middle position. We can't have it opening half or opening the valve 10% or 20%. That is not possible for an on-off controller. That is the reason why we are now going to study another important control scheme. Now, this is the control scheme that you will also be seeing used in the industries. That is called as the PID controller. What is the word? P stands for proportional. I stands for integral. D stands for derivative. So this is a concept which we have to build up slowly. Though I am showing you PID controller together, we can look at each of these controls separately. Okay, so basically a PID controller consists of proportional, integral, derivative. You may remember it is a PID controller. Remember, P stands for proportional, I stands for integral, and D stands for derivative. Now these are all mathematical terms and we have to see how this mathematical equation can help us to have a control strategy which will give us optimal response. Optimal response means the correct response that is needed for the controller. So here you see the block diagram now. You have the process. The process variable is measured by the sensor. Sensor output is called as a measured process variable. It is going to be compared with the set point and accordingly this controller will take action. The output is called as a controller output. It will be given to the process and the process will make sure that the set point is kept equal to the process variable. But because of disturbance, this condition is violated and then this whole circle has to continue. Now we will go into understanding about the PID controller, each controller block separately. Okay. So when I think of a PID controller, what actually we are doing is the error signal is fed to each block separately. So we are splitting the PID controller into 3 blocks: proportional, integral, and derivative. And the output of all the 3 actions is going to be added together and this becomes your control output. We have to look at each of these strategies separately.
Oh,
Now,
this is
start.
best than on-off, doctor.
This is better. This is what we should use always.
Yeah, it is best
Yes.
than on-off.
Yes, we can manipulate. We can make the valve to open 10%, 20% using this controller. So this starts with the error, of course, and you know what is the error? It is set point minus the process variable. So out of these, the first one is called as a process proportional controller. Now let me also explain to you the mathematics of these. You know what proportional means. Okay, that means the proportional controller is producing an output that is directly proportional to the error. So the output of the controller, if it is a proportional controller, means whatever error is felt by is being fed into the controller, correspondingly it will produce an output. So if I write the equation, it becomes Kp into E of t, where Kp is called as the gain of the controller. Kp is called as the proportional gain. So usually what happens here is, in the proportional controller, we are multiplying the proportional gain by the error signal. Okay, so this is how the proportional controller works. So every time there is error, what you will notice, now let's say if the error is equal to 0, what will be the output of this controller? If the error is 0, what will be the output of the controller?
100.
100. So Kp multiplied by, I'm saying that the error is 0. Kp multiplied by 0 equal to?
0.
0. So when there is no error, this controller doesn't produce an output. As the error increases, the proportional controller's output will also increase. But how much it will increase will depend on the value of Kp. Okay. So if the gain, now there are two conditions. Like I told you, according to the value of Kp, the output can be increasing fast or it can be increasing slowly. Now, if you want the output to increase fast, what do? Use a very high gain. That means you keep the value of Kp very high. But if you keep the value of Kp very high, it makes the process to become unstable. What is the meaning of unstable? Unstable means the process variable, okay? Suppose I'm going to use a proportional controller. If I'm drawing the graph, this is my set point. Here I have time. Okay, this is my process variable. So I want the process variable to always be on this line. No? That means the process variable should be the same as the set point. But that's not what happens. So if the value of Kp, okay, according to the value of Kp, the process variable is going to be increasing or decreasing. It's going to be increasing or decreasing. Now, if you keep the value of Kp very high, you will notice that the process variable is going to change rapidly. It's going to become like this. It will almost become like on-off controller. So, a proportional controller with very high gain is unstable, means it is becoming like an on-off controller. Okay. At the same time, if I keep the value of Kp very low, if I keep the value of Kp very low, if I say that Kp is very low, then what will happen? When you look at this equation, the proportional controller's output is Kp multiplied by the error. So for a large error also, the proportional output is going to be slow. So what you will see that whenever there is a disturbance, it is going to take a long time for the value to come back to the set point. Okay, so the proportional controller is dependent on the value of the proportional gain because error is multiplied by it. Too much gain makes it unstable or makes it like an on-off controller. And very low gain is going to cause the system to be slow. Both are not desirable. So we have to design we have to manipulate, we have to design the controller such that the KP will make sure that the proportional controller's output is going to take the process variable back to the set point whenever there is a disturbance. What happens actually, okay, so this is according to time, and this is your process variable. Let us say because of disturbance, and this is the point, set point. Let us say that because of some disturbance, okay, so initially your value was at the set point, then because of disturbance, the process variable increased. Now what do you expect? You expect the controller, after the control action, you expect that it should come back to the set point. So this duration or time taken for the proportional controller to go back to the set point is dependent on the value of KP, which is giving you two situations, either making it slow or making it too fast and unstable. Both are not desirable. Now the problem with this proportional controller is that whenever there is an error, then only the controller is producing an output. If the error is small, the output is also going to be small. Now, the biggest disadvantage of the proportional controller is because of the control action and because it is depending on error, always, okay, always at the end of the proportional output, you will always have some error that is standing. Some error will remain in the system. When we use a proportional controller, there will be some error remaining in the system. So to remove out that problem, we are thinking about an integral controller. Now, first of all, let us understand what is the meaning of integral. You know, in mathematics, there is integration, this sign. Let us say this is error into dt. Integration. Integrate means you are carrying out an operation of summing until this value becomes equal to 0. What is integration? Integration is continuing to sum, go on adding till you are not left with anything. Okay. For example, in school we have studied about integration. You have an object. Okay, let's say you have an object that is having an odd shape. If I ask you to find the area of this odd shape, how will you find the area of this odd shape? How is it possible to find the area?
It is difficult.
It is
because
difficult.
not have permanent
Yes.
shape. Yeah.
But remember that there is a very simple method. What do? We use a graph paper. You know what is a graph paper, no? Graph paper is divided into squares. According to centimeter, like that, it is divided. Okay. So what you will do is, you will draw the same thing in this graph paper. Okay. Now, how you will find the area? You will count all the full squares. How many full squares you have? That you will count. Then you will write that number. Number of full squares. How many? Then you will count the half squares. Okay, these are half squares. This was also full square. So these all you will count and write the number of half squares. Like that, you will continue this process till you have covered the entire area. Because you know the graph paper is divided into centimeter and millimeter. So you can count each of those squares. So like that, you will go on adding all the area, all the covered area in terms of centimeter and millimeter. Add all of that up, and that gives you the area of this irregular shape. This is how we do it. In school, actually, you have done it, but you don't remember now. You have taken a leaf, placed it on a graph paper, draw the leaf, and then calculate the area like this by counting the half squares and the full squares. Now, why I'm explaining this to you? Because this whole process that you're carrying out here of adding the half square, adding the full square, adding the 1/3, 1/10. That whole process that you're doing is you are doing summation, you are doing plus, 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 until you don't leave out any part for this calculation of the area. So that is the meaning of integration. So what we are doing here in this process is called as integration. You are integrating the entire area. So if you look at it from the top, what you are doing is you are carrying out the integration. You are picking up all these areas and bringing it to one focus, which is the total area. This is called as integration. This is what we do mathematically in integration. So why are we talking about integral controller? We are talking about integral controller because the controller will go on calculating the output until the error becomes equal to 0. So integration is continue to summation, continue to do the summation until nothing remains. Same way here, when you find the output of the integral controller, you are going to multiply the integral gain by the integration of the error, and this will continue till error becomes equal to 0. So the advantage is that you will make sure that the desired value has been reached, which is not possible in proportional. So what do? We take the integration of the error as well. We find the proportional output and we add it to the integral output so that there is no error remaining in the system. Unless there is a disturbance, there should be no error. Okay. Now, what is the disadvantage of this integral action? So integral action is good. Okay. The error is found, multiplied by the gain. The gain can be adjusted to drive the error to 0. So again here, the gain, which is Ki, the integral gain is called as Ki. If you keep this integral gain to be large, it will make the controller to go on. It will make the integral controller to go on doing the integration. It will continue, 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 continue. And what will happen? It will bring too much output. If the output becomes too much, what will happen? Your valve will open completely 100%. And because the integral output is increasing, you cannot go beyond 100%, correct? The valve can open maximum 100%. So it will remain there. And over a period of time, it will get stuck there. Because it is pushed to the 100% position for a long time. So the valve is going to remain open for a long time, and sometimes, you know, it will make the temperature or the flow to go on continuously, which will also give you a problem. So we have to make sure that the gain is adjusted to make the error to go back to 0 in the required time. Simple example I can tell you, you know of this toy, you know, the children are playing, which is having a key. When you turn the key, this doll will start to dance, or this dog, it will start to dance. So if the key is, you turn the key, as much time as you have turned the key, the dog will dance or it will jump. So the moment the time for the key is over, it will stop. Now think of the situation that you are going on turning the key continuously, turning, and it will break. So that is what happens in the integral action also. If you don't adjust the gain, the integral controller will make the final control element to go to its extreme. If it goes to the extreme, you will have an undesirable situation. So you have to adjust the gain to make the error to go back to 0 in a required time. Now, because of this integral action, the problem is that the integral action is slow. It is making the process to become slow. Because if you draw the graph of time versus the process variable, whenever there is if this is your set point, maybe it is at set point, and then because of disturbance, the process variable increases. And then for it to go back to the set point, it is going to take a very long time. Or sometimes what you will notice is that the value will increase, then because of the integral action, it may become less, and then it will increase, and then it will stabilize very slowly. It's going to take a long time, which is undesirable. That is the reason why we go for another control action that is called as derivative action. So derivative is another mathematical term which all of you know about. You know in mathematics what is derivation means. Whenever, if I want to calculate the speed, what do I do? Rate of change of the distance divided by the time. Or let's say if I want to calculate the acceleration, what do I do? Rate of change of speed with respect to time. What I am doing here, I am actually calculating d by dt. This d by dt means you are finding out the derivative. Okay. So what is meant by derivative control? Derivative control means the output of the derivative controller will be kd multiplied by the derivative of the error. You are going to find the rate of change of error multiplied by the derivative gain. So here you have the derivative gain, which is kd. So the advantage of using the derivative controller is that you are finding the rate of change of the error, which will be making the system to become fast. Okay, so like it's written here, the derivative controller is used to improve the transient response by reducing the overshoot. So what it actually means is, in figure, if I show you, suppose I have I'm drawing the graph for the process variable. Let us say initially it is at the set point. Then because of disturbance, it is rising up. Okay. Now, when you use only proportional controller, what will happen? When you use only proportional controller, then it will come back to, but it will remain at a distance because there is some error remaining. Now, if I am going to use the integral controller, then what will happen? Then the output, okay, then the process variable is going to come back, and then it is going to increase, then decrease, then increase and decrease, and then it is going to settle down. But if I'm using a derivative controller, it will make the variable to come back to the original value very fast without any error. Also, it will be faster. Okay. So the derivative action is used to improve the transient response. Transient means it is changing. So it will make the process variable come back to the set point fast. Okay. And it also reduces the overshoot. Now this reducing the overshoot means what? Let us say, okay, there is a disturbance because of which the controller output is producing an output. This is because of the integral output, okay, integral controller. Then it is going to reduce, increase, like this, and then it is going to stabilize. This is the output from proportional and integral together. So here you see there is too much time taken. Plus, in the first, there is something that is called as overshoot. Overshoot means the value of the process variable is going way above the set point. Why does it go like this? Because the integral action is producing an output dependent on the error. In the first time, it will see too much error. So it will produce too much output. Okay. Now, if there is overshoot, the problem will be, what will be the problem of overshoot? Maybe you are opening the valve too much. Maybe you are allowing too much water to come in, or maybe you are allowing too much power to the heater. So this is undesirable. You don't want overshoot. But instead, if I'm going to use a PID controller, then what you will notice is that it is going to settle down faster with less overshoot. The overshoot is small. So this is PID controller, and this is only the PI, only PI. So that is the advantage of using these three controllers. Now, if you see, The most common, we are combining these three controllers together. Okay, so I can use them separately also. I can have only proportional controller. Sometimes it is used wherever you can tolerate the error. Like in level control systems, we can go for only proportional controller. The most common used is PI. PI is most commonly used for all control systems. PID is also used especially when there is temperature, composition, when you have to make sure there is no error and you want the control variable or the process variable to come back to the set point fast. You have to use the PID controller. And PD, this combination is very rare, only for servo motors. When you want the motors, no, especially the ones that are used for electrical applications, we will use PD, but very rarely. In our area of work, we use mostly the PI or the PID. Okay. So this is now the total block diagram of a process control, closed loop process control system with the PID controller. So you can see here, first of all, the process output is measured. There is a sensor block here. I have just not put it because we're just looking at the mathematics. So the process variable is measured, compared with the set point. The error value is given to all the three controllers simultaneously. The proportional will produce an output depending on this equation, which I have told you. The integral will also produce an output depending on this equation, and the derivative will also produce an output depending on this equation. So the final output that you measure is calculated by this old rule. What is the rule? It is, this is Kp. Kp into, yeah, this is Kp into E error plus Kd into the derivative of the error plus Ki into the integral of the error. Now there is a new term that I have added here. I'm going to explain to you about this. Okay. So what is the equation that I wrote for you? The equation that I wrote for you is, let me write it again so that you also have a practice. Equation is Kp into E of t. What is E of t? E of t is equal to set point minus the process variable plus Kd into dE of t by dt plus the integral, that is Ki, into integration from 0 to time t et of dt. Now plus I am adding another term that's called as Ps, which is a constant. Okay, Ps is a constant. So whenever the error is going to be equal to 0, the output of the PID controller will be equal to Ps. Okay, why do I need this situation? Why do I need the output to be at Ps or at a constant value? So let us see this example. Okay, I'm going to give you an example. Let me see if it's there in your handout before that. Okay, I need to give you an example. So we go here. Okay, let us say I have a furnace. You know what's a furnace? No? Furnace is where air and fuel is combined to give you burning. So I have a furnace, okay, and we are measuring, there is an exhaust gas here. Exhaust gas, because in a furnace you have burning and then the exhaust, the gas has to be exhausted. No? Then here you have a valve, okay, which is allowing the fuel to flow in. Here I am measuring the temperature. Okay, I am measuring the temperature. The output from this temperature is, I am measuring the temperature. The output from this temperature is given to the controller. Okay, is given to the temperature controller. The temperature controller is also given the set point. Okay, and according to the decision, this temperature controller will come and manipulate the fuel line. Okay, so this is a very simple example I'm showing you. So here you have the process variable, here you have the set point, here you have the controlled output. Yes? Anas, are you saying something? Anas? Okay. So here you see all the blocks, but I put it in the form of a picture. So here you have the measured value, here you have the set point, here you have the controller output, which is manipulating the valve. And what is being manipulated? The flow of gas is being manipulated, and the furnace is going to be maintained at a particular temperature to allow the allow the furnace to be burning according to the required temperature. Okay. So in this case now, what I'm trying to explain is why we need that PS. Okay, why do we need a constant output? We need a constant output because even when there is no error, that means when the process variable is equal to the set point, the controller output should be equal to PS, because you want the valve to be open. Do you want it to be closed? No. You want it to be open maybe 50%. Because you have to allow the fuel to come in. No, if you don't allow the fuel to come in, there will be no burning. So this is called as the optimal response. Optimal response means the controller will take a decision to allow the valve to remain open so that this condition is satisfied. And that is why we always need to have a constant output. If you don't have this constant, your valve will close or your valve will become fully open. There is no in-between position. So usually we allow the output, that is constant output, to be about 50% so that the valve can be half open. So any time the error is becoming greater than 0, you will try to, when will the error be greater than 0? How is error? Error is equal to set point minus the process variable. So when the error is 0, whenever set point is greater than the process variable. If the set point is greater than the process variable, means you need more heat. So the valve will open more and allow more fuel to come. Whenever the error is less than 0, when will the error be less than 0? When the process variable is more than the set point. At that time, what do you want to do? You want to close the valve. So if it is constant at 50%, you can go from 50 to 100 or you can go down from 50 to 0. So to have this possibility of throttling between 0 to 100, we are maintaining a constant output when the error will be equal to 0. So that is the reason why we have a PS, which is a constant. Now I'm showing you the response of a PID controller for varying values of Kp and Ki and Kd. Or it is comparing between P, Pi and PID. I've already shown this graph to you. So let's start with the one in the middle. That is this one. This graph is when you have Kp equal to 1, Ki equal to 1 and Kd equal to 1. That means we have a PID controller. Okay. Now in the same PID controller, I'm going to show you what is the effect of changing Ki. For this PID controller, when I change the value of Ki to 0.5, from 1 I'm reducing it to 0.5, you see the response is becoming very slow. And if I increase Ki to 2, the response is making an overshoot. This part is called as the overshoot. Okay. So in a PID controller, by adjusting the value of Ki, you are able to see the different responses where Ki is small. If the Ki is less, it is becoming slow. Ki is more, it is becoming too much overshoot. And all this can be taken care of by the introduction of the Kd controller, Kd or the derivative controller. So this brings us to the end of the PID controllers, only the control strategies. And these are some of the industries which they are used in. PID controller, automatic car steering. This was started with Honda. Honda started first and then now all cars have it. Then the second example is motion detector of a seismometer. You know what is a seismometer? It is used to check earthquakes. So whatever I'm ticking are the more important applications. Water and oil level monitoring in the tanks. You need to make sure that the tank is neither becoming empty nor becoming overflowed. So you need to have a controller. Then you can use it for automated inspection and quality control. You can check the quality of your product by checking the dimension. Okay, that is if it is a mechanical tool, or in the case of checking the size of a package, checking if the bottle is correctly labeled and bottled properly, sealed properly. So that's automated inspection. We go in for the use of controllers. Then in chemical process control, we are going for flow control and temperature control, because you need to make sure that you are able to obtain the fuel that is desired. Then you have automatic control of material handling. If you have seen these packaging units where let's say there is one juice packet and there are 12 juice packets put into another box, they made like a bullet. So that is material handling. And also packaging for dispatch, how medicines are placed, like you have a strip of medicine where the capsule is placed inside an air bubble. So all of that is automatically done, and that automatic control is possible because you are implementing either the proportional, integral, derivative control or the on-off controllers, and to ensure safety during manufacturing processes. So like the example I gave you here of the exhaust gas, I'm placing a valve here. Okay, so this valve has to work. If this valve doesn't work, what will happen? All the gas will be trapped inside the furnace and you will have an explosion. So we need to have control also of, or we need to ensure safety by making sure that all the exhaust gases or the safety valves that are placed here are properly manipulated or properly adjusted so that they open and allow the gases to flow out. Okay, so this is all about the different control schemes I've explained to you. I started with on-off controllers. That is because they are examples of closed loop systems. We have seen two clear cases, on-off controls on open loop systems and closed loop systems. Under the category of closed loop, we studied control system. Okay, one category open loop, another category is closed loop. In the category of closed loop, we studied on, off, and also we studied PID. I've explained to you what is P, what is I, and what is D. See, actually, the explanation that I'm giving to you is like a small capsule, like a small medicine. We have to discuss this more in detail by writing equations, by calculating problems and so on. But since we have more outcomes to cover, I have made it very concise. Okay. So this brought us to the end of discussing about controllers. So if you look at the whole block diagram, I'll draw the block diagram one more time. This is the process. Here you have the process variable, the control variable. It is measured by a sensor. Then we call it as a process variable, measured process variable. This is given to the summing point where you have the set point, and here you have the minus sign. So you're basically obtaining an error. Error is given to the controller. The controller output is then given to the final control element. And here you have the manipulated variable. This is the block diagram. And we know what are the examples of processes: water heating, crystallization, evaporation, distillation. They are all examples of processes. Examples of variables: level, flow, temperature, pressure, composition, density, humidity. They are all examples of variables. Then you know also the different type of sensors for measuring them. Then you compare it, you go to the controller block, the error is given to the controller. Here you have seen two cases, on, off, and PID. The controller output is then going to the final control element. So now to understand how these final control elements work, we are going to focus our attention on the final control element. So the next part of this chapter is talking about final control elements. Now there are many final control elements. Like I told you, we can have heater, we can have pump, we can have motor. But out of all of these, the most common final control element that you are going to deal with is a valve. Okay, so here I have mentioned about the final control element. They are devices that complete the control loop. They will link the output of the controlling element with their process. So basically you are linking the controller to the process through the final control element. So the final control element receives the output signal from the process controller and adjusts accordingly the value of the manipulated variable. And it adjusts it so that the energy entering into the process is going to bring the control variable back to its set point. Now, when you read in words, it sounds quite difficult for you. But if you think in picture, if you think of what's happening from the block diagram that I showed you, what does the final control element do? It takes the instruction from the controller and it manipulates the, or it adjusts the manipulated variable until the process is able to produce an output that is going to match the set point. So the final control element is very important because it is directly influencing the process. Examples of final control elements are valves, this is one, dampers, pumps, and heaters. Now valve and damper is like have similar functions. Dampers, okay, just let me check if I can give you an example of a damper. Okay, so you see this picture that I'm showing you. This is an example of a damper. Okay, so you see here what's happening. When I move this, are you able to see it? Boys?
Yes, Miss. Yes, Miss.
Yes. So you see here, these are the levers. Now, and they are all linked together. So when I move this, what will happen? When I move this part, what will happen? When I move this part, what will happen? This can be either opened or it can be closed. So this is an example of a damper. Okay. So dampers, then you have pumps. You know, you were studying about pumps, centrifugal pump, rotary pump, positive displacement pump. What does a pump do? Pump is actually adjusting the flow, okay, and adding pressure. So you can have, you know, of the example of a pump. Electrical heaters are very standard, commonly known to you. Out of all of these, we are going to focus our attention on a valve because it is regulating the flow rate of a liquid while the damper can regulate the flow of air and gases. Okay, so we are going to focus our attention on control valves. They are the most common type of final control element in the process. That's the reason why we are focusing our attention on control valves. Now, again, let me give you a proper picture of the final of the valve. I'm sure you see this picture now. So what you're seeing here is an example of in a pipeline. You are seeing, yes,
valve.
yes, yes. So in this pipeline, you can see this blue color. This is a valve. Okay, and this valve is what we're going to study, because you are going to see hundreds of them in the flow lines that you're going to work with wherever you're going to work. Okay, so here you see this particular valve is it's this blue device, or this blue is the valve, and it is this part which is coming in line with the pipe is called as the valve body. And what you see on the top here, this is called as a valve actuator. So basically the control valve is consisting of two parts, the valve body, and this is called as the valve actuator. Okay, so the control valve that we are going to be looking at in detail is depending upon how the valve can be opened and closed. We have to see that. So basically a control valve is with hydraulic, pneumatic or electrically. See, because if you look at this picture, this valve, if you want to open the valve, that means if you want to push it open, this actuator has to move up. Actuator has to move the valve, the stem inside up. Then only it will allow the flow to go. So where will that power to open this valve come from? Okay, the controller is sending the decision, but the controller is maybe an electronic one. Maybe the signal coming from there is a standard signal of 4 milliampere to 20 milliamperes. Now that is not enough to open the valve of this size. So usually the valves are actuated pneumatically or hydraulically or electrically. You have to give external power. This power can be either by compressed air, by liquid under pressure, or by an electrical signal. Okay, and the power has to make the valve either go from off to on or on to off, or it should be able to open the valve in percentages like 10%, 20%, 30%, like that. Okay, so we are not using valves only for shut-off. We are also using it such that you can throttle the flow. That means the control valve that we are putting in the pipeline should be able to withstand high fluid velocity and turbulence without maintenance. It should be able to continuously withstand. Okay, so let us see what are the parts of this control valve and how does it work. So what I am showing you here in this figure 4.10 is the valve body of a globe type valve. There are many types of valves. There is globe valve, gate valve, needle valve, butterfly valve. Many different types of valves are there. What I'm showing you now is the globe valve, which is, and also I'm showing you only the valve body, the lower part. If you see from here, only this part I'm showing you now. What does this part consist of? Okay, so here you see there is a valve stem and a valve plug. Now this is the opening through which the flow can pass through. If the valve stem is pushed down, the plug will close. When it closes, no flow can pass through. This is the valve being fully closed. That means the valve body is having inside it the seat. This is called as the seat. Then it has the valve plug, it has the valve stem, and this whole thing is called as the valve body. I've shown you two pictures of the valve being fully open or the valve being fully closed. So to regulate the flow, we are using the concept of a variable orifice. Orifice is a restriction. So there is a restriction, but the size of this restriction can be changed by the position of the valve plug. You may completely seal it or you may keep it half open. So if it is in this position, some amount of flow will be possible. If you move this further up, more flow will be possible. Okay. So you are regulating the flow of the process fluid according to the requirements of the process. Now, how this valve plug can be pushed up or down? It can be pushed up or down linearly. This is called as linearly, or it can be pushed up or down by threading it. I can turn it. You know, like you fix the screw, you are turning the screw. That is a rotary motion. So either you can have a linear motion or you can have a rotary motion. Okay. So the body of the control valve is defined as the part of the valve that comprises the main boundary, including the connecting ends. They are basically classified into two types depending on the movement of the valve closure, linear and rotary. Okay, so I will stop class for today here, and in the next class, that means the next Wednesday, which is supposed to be the last class, I will complete the chapter for control valves. Okay, so we will come to the end of this chapter. Of course, I'm not going to take this part. Till here we will complete, and that will be the end of the portion. Okay.
Which chapter 5 does it?
Yes, there is. What is that?